Okay, good afternoon. So today we are going to conclude the part on switching theory. So is there any question about rearrangeable non-blocking networks and the Slepian-Dewey theorem? Everything's clear? Okay. So, as you may expect, now we are going to have a look at strict sense non-blocking networks, again, multi-stage implementation. And in this case, we can also consider two-stage architectures beside the three-stage architectures. So let's start with the two-stage architectures. And we are now in the case of full connected network. So again, we have two stages of switching matrices. Each matrix of a stage is connected to all the matrices of the next stage. We start from this initial architecture. Okay. So here we have the fully connection with a simple single link between each matrix of the first stage and matrices of the second stage. This network is clearly fully accessible. We assume that all these switching matrices are, for example, crossbars or strictly non-blocking blocks. And you have full accessibility because from the matrix of the first stage, you can reach all the matrices of the second stage, and the total number of outlets of the matrices of the second stage is equal to the total number of outlets of the network, which is capital M. Okay. The question is if this network is also non-blocking, and in particular if it is strictly non-blocking. And actually it is blocking for sure. The reason, we have already introduced it maybe in a less formal way, but the reason is that since here you have one link for each pair of matrices, once you use that link for one connection, then you're done. You cannot connect anymore the two matrices of the pair for another connection. Okay, but the matrices are not splitters or and combiners. They have multiple inlets and multiple outlets. So from a matrix of the first stage, you don't have a single connection, you have many, and out of the matrix of the second stage, you have m outlets. So if even two inlets of the matrix of the first stage have to be connected to two outlets of the same matrix of the second stage, you have internal block. Okay, so this is why this architecture is blocking. What is the workaround to make it non-blocking? It's very easy. We just employ link dilation. So instead of using a single link for each pair of matrices of the first and second stage, you use D-links, okay, D-parallel links, D-links in parallel. Each one is able to carry one connection. And now the question is, how many connections, what is the maximum number of connections that we can set up from this matrix of the first stage to a specific matrix of the second stage? Clearly, the number of connections, the maximum number of connections, is the minimum between small n and small m. Okay, where small n is the number of inlets of each matrix of the first stage, small m is the number of outlets of each matrix of the second stage. So once you make this link dilation greater or equal to the minimum between small m and small n, you obtain a non-blocking architecture. Okay. More, this is also strictly non-blocking. Why is it strictly non-blocking? We are in the similar situation that we have in the, for example, crossbar tree. Okay. In the crossbar tree, each internal link is dedicated to a pair of inlets and outlets. Okay. Here, each internal link which is dilated d times is dedicated, so each group of links, each bundle of links of d links is dedicated to a specific pair of matrices in the first and second stage. See if D complies with that condition, then you will never have internal blocks. Okay. So basically, this is a strictly non-blocking network and strictly non-blocking architecture. Obviously, the cost increases compared to the fully connected two-stage network with a simple single link between each pair of matrices. How much is the cost? Okay, we can assume that here we have crossbar blocks. Okay, so the cost of each matrix is in the first stage n by r sub 2, and its last stage is r sub 1 by m. And then you simply multiply this by d and in both stages, and then you sum the two stages. So that's C equal to that expression is the cost. Assuming the simple case where you have symmetrical architecture, so it's basically a square, so capital N is equal to capital M, small n is equal to small n, and then capital N must be equal to R by small n, which is the number of matrices in the first stage, which is also equal to the number of matrices in the second stage. If you replace that expression inside the value of the expression of C, you obtain that C, the cost is 2 by n squared, okay, which is exactly the same as the crossbar switch, as the crossbar tree. And actually, as I've already, you may imagine, the crossbar tree is a special case of this architecture, where you have small n equal to small m equal to 1, and therefore d is equal to 1. So you fall back to the fully connected case. Okay? Questions? These are two examples, one example. Here you have the starting point, which is a fully connected network with 3 by 2 and 3 by 5 matrices in the first and last stage. You have to take the minimum between 3, small n, and small m, in this case between 3 and 5, so the minimum is 3. This is equal to the dilation that you have to use in the internal links. So if you use links that are dilated 3 times, then you have a strictly non-blocking architecture. Okay. Okay, this is the calculation of the cost in that architecture, assuming that you have the blocks implemented as EGS networks that we have seen previously, so the costs are quite similar in terms of result. You can look at these calculations by yourself. That's nothing very important. So let's now go to the 3-stage case. Here we have the same, the similar architecture that we have already met in the Slepian-Dewey theorem. So 3 stages of matrices. We have to understand how we can dimension these matrices in terms of number of inlets and outlets and number of matrices in each stage, so to obtain a strictly non-blocking architecture. And the answer to this problem is the so-called Clos theorem or Clos network. So imagine you have a three-stage network, which is in the general case n by m with matrices that are R sub 2 matrices in the central stage, and matrices in the first stage have small n inlets. In the last stage have small m outlets. Then the question is how many matrices in the central stage I have to deploy. The answer is the Clos theorem. So the three-stage network is three-sense non-blocking if and only if the number of matrices in the central stage is greater or equal to the n plus small small m minus 1. That is, that becomes 2 small n minus 1 in the square case. The proof of this theorem is much easier than the proof of the Slepian-Dewey theorem. We just have to consider the worst case. The worst case scenario. Again, we start with the test of blockingness, and that means that the network is non-blocking if given an idle inlet and given an idle outlet, we can connect them with a new connection. And it will be strictly non-blocking if we can do this in all cases, regardless of the set of the status of the other connections that are already set up. So we have just need to take one matrix in the first stage and one matrix in the last stage, and we assume that the two free inlets and outlets are in these two matrices. So we have one free inlet in the first matrix, one free outlet in the last. In the worst case, from the matrix of the first stage, we will have n minus 1 connections already active. Okay. And in the matrix of the last stage, that is hosting the free outlet, we will have n minus 1 connections already active. Each of these connections that are active starting from the matrix in the first stage have to be rooted in matrices in the central stage, as well as connections that are arriving to the matrix of the last stage are coming from matrices of the central stage. Now, the worst case that you see there mapped is when the matrices, the connections that are starting from this matrix are connected to matrices in the central stage that are totally different, disjoint from the matrices of the central stage used by the connections that are going out to the first stage matrix that we have selected. Okay. So the two sets of matrices connected in the central stage are not overlapping, and therefore we have n minus 1 matrices hosting connections that are coming from the first stage, n minus 1 hosting connections that are going to the last stage. So in total we have n minus 1 plus m minus 1 matrices that are taken. In order to set up the new connection, we need an extra matrix. Okay. So if we need an extra matrix, it means that we need n minus 1 plus m minus 1, that becomes n plus m minus 2, plus 1, n plus m minus 1. Okay, that is the proof. This condition is necessary, obviously, because otherwise I cannot set up the new connection. It's also sufficient because it is the worst case. So you cannot imagine other configurations that are worse than this. So this proves that completely proves the theorem, and it's very easy. So what is the cost of this architecture? We can assume that matrices are all implemented as crossbars. So each matrix is A by B has a cost in a number of cross points that is A by B. And if you count matrices in all the stages, you come out with this expression that is general. You have this first expression on the left. For the rectangular case, now if you want to specialize to the square case where small n is equal to small n, then you come out with an expression with a single incognita, which is small n. Okay? And capital N is a parameter. So we have 1 degree of freedom, as in the case of Sleepy and Do-With. We have to decide how we want small n, and to obtain the optimal value, we just can calculate the derivative of this cost expression as a function of small n. And the result is that the best value of small n is the square root of n divided by 2. Okay, capital N divided by 2, yes.
Even if reduced state interpolation becomes inactive, so what will happen to the matrix? Will it get obsolete or stay there?
If one of these connections becomes inactive, the matrix stays there, of course. Then, if it becomes inactive, this link between this matrix and this can be used by a new connection. Be careful, because I said in this picture you see the matrices, okay? But the real bottlenecks are not the matrices, are the links between the first and the second stage, and the links between the second and the third stage. Obviously, this matrix does not only host this connection that is active, because the matrix has several inlets and outlets. You will have other connections, but this matrix is connected to this specific matrix in the first stage just by one link. Here you don't have link relation. So once this link is taken, you cannot set up other connections. So the picture is complete. You show, you count matrices, but actually you have always to think that the limiting factors are the links between the first and the second stage. So this is the best value of n. You can decide, and the corresponding minimum cost that you have this. And we can compare this minimum cost with the minimum cost of the rearrangeable non-blocking architecture we have calculated before after the theorem. And it comes out that strictly